Let's just start. So hello everyone. I am Adrian Cristian Nicolaescu, or Chris. Um, I am a senior research associate at the University of Bristol in the Smart Internet Lab, and I participate in 5GASP as the Work Package 6 leader, and we um, have managed, and I will be coordinating this webinar. 5GASP is a European Horizon 2020 project, part of the ICT 41 umbrella. It aims at shortening the idea to market process through the creation of a European testbed for SMEs. It aims for a fully automated service, self-service oriented, secure and trusted environment to foster rapid development and testing. We are looking to provide to also provide new and innovative 5G network applications built using the 5G NFV based reference architecture. And the main areas in which these network applications have been developed were in automotive and the public protection and the disaster relief areas, or PPDR, that is. We are aiming effectively to offer software support for continuous integration and continuous development and with the CI/CD process specifically for VNFs. And we are looking to also provide SMEs with effectively a way to capitalize on the 5G market. Without further ado, we will today tackle the automotive industry area, and we will have an introduction from Dirk Hetzer, who is part of the testing company that is involved in 5GASP called the NTC in Berlin, and I will let him introduce himself right now and introduce the project. Thank you very much, Dirk.
Chris, many thanks for the nice introduction. I will start to share at least one slide. Don't be worried, it's too much. Yeah, as already mentioned, I'm working at ENTC, this is a small test lab here in Berlin, and I have also history in Deutsche Telekom T-Systems for automotive department, and this is the reason to give you a very short introduction why this automotive area is so important in the connection with mobility, and why 5G ASP is possibly a very valid building block for this environment or this developments in the future. Yeah, a car you can see here on the left side has today many connections to different other parts of the infrastructure and different other parts during the driving, beginning with, let's say, standard communication for infotainment, going to connections for roadside infrastructure like traffic lights or parking informations. And next big important part is then the connection from car to so-called OEM backends for dedicated OEMs, or also for third-party backends. Then, of course, interaction with other partners in the traffic itself. And of course, in near future, the very big question is how to come then to autonomous driving and what it means also for connectivity. And here you have this picture that local sensors from cars have limited possibilities, but for real autonomous driving, you need a longer view on your trip, on your street in front and behind you, and other connections to cars in front of you, other vulnerable road users, bike users, and so on. And all this can only be supported with very strong network infrastructure. And it means the future of 5G in this environment is to connect all these parts together, to have new functions like prediction of quality of service, like guaranteed service with dedicated slicing, like precise positioning, like mobile edge computing to reduce latencies. And all this stuff will lead then to additional functions, additional applications. And these applications, of course, have to be very safe, have to be very strong in security areas. And our project 5G ASP will support this development to test all these different applications. Of course, not all in the project. We have a selection from about 10 applications to test in different areas of this 5G requirements. To give you examples, to test security issues, to test performance issues, to test other 5G possibilities like slicing. And all this is done in a so-called automated environment, an automated test environment to be integrated in a CI/CD pipeline. And in the next presentation parts, you can learn how this is then done in our project environment. So far for the introduction. Many thanks.
Thank you very much, Dirk. That is perfect. We will also have a questions and answers session after, so we will be looking forward to that after the presentations of 2 network applications developed in this vertical. The first presentation will be given by Ana Hermosia, and the second will be by Christophe Courtier from and I will introduce each one of them in turn. So Ana is currently a PhD candidate in the Department of Information and Communications Engineering at the University of Murcia. She's also an industrial researcher at Odin Solutions, Odins for short. She has experience in cloud virtualization, IaaS, infrastructure as a service, NFV, 5G, and of course, layer 2 and layer 3 network management. She's participated in a few ICT 41 projects, including Inspire 5G Plus and 5GASP, and she's working on Gaia 5G as well. Ana,
Hi.
the floor is yours. Thank you.
Okay, thank you. Thank you, Chris. Okay. Well, as Chris already told you, the idea of Odin Solutions is SME located in Murcia. Before the 5GAS project, we hadn't any experience with 5G networks. It was our first project concerning 5G. And as Chris already told you during the introduction, the idea of 5GAS is to ease the process of SMEs to adapt to a 5G environment. So we are the best example for the purpose of this project. Basically, to work here, and what I'm going to present is 2 use cases we had, and how they were before the adoption of the 5GAS procedures, and how we adapt our previous solution and adapt that to a 5G environment, and how it could benefit from all the guidance 5GAS give us. Basically, the services aligned into the automotive vertical was the virtual onboard units called the ODU, that it's the virtual digital twin of the physical ODU located in the cars. So the idea is to deploy a virtual one located into the edge, so you can use it and access that virtual OBU instead of the physical one to ease out the processes. Also, we have another use case that is the one that I'm going to show you, and based on the migration of those virtual OBU, due to the fact that the cars are moving. So you need to change the location of the deployed virtual OBU when the car moves and changes its location. So this is our testbed. We work in joint collaboration with the University of Murcia. So this is the 5G scenario and the real testbed we have. Located into the campus. So we have different antennas, different sites. So we can prove and evaluate how a real car is moving and changing its location using 5G. So the use cases will be to follow. As said, what is the virtual migration network application? As said, the idea is to having the physical view, the virtual one, and using the virtual one as a sheet. What was the problem of the first version of this application? It was very dependent on the underlying infrastructure. It relied strongly on SDN controller, and it was highly dependent on how the infrastructure was, as the SDN controller needed to know exactly the characteristics of the infrastructure to be able to change and adapt and resending and configuring all the flows. So it worked, but it wasn't interoperable or dynamic, let's say. So the idea of this is evolving and upgrading the use case to a 5G network environment, adopting the 5GAS methodology, adding the test that 5GAS also offer, etc., etc. So as said, before it was strongly rely on the SDN controller, but now instead of using that, we'll be using a component of a 5GAS network called the network exposure function, called NEF, that is an entity in a 5G infrastructure, 5G core, that it's offered for third parties to retrieve information from the network. In that, for example, the network statistics, the quality of service, or the location of the device. This is the value we are retrieving, because we need to know the location of our device, in this case, the physical OBU, the car, to know where it is and if a migration is required, and therefore starting it. So this was the original architecture and of everything. So we adapted it through the net. And the problem with this was that currently there's no NEF implementation yet. No 5G core right now is implementing this functionality. It's defined on the standards, but no one offers that functionality. So to solve this, we proposed and we presented two demos. One, through the 5GAS CI/CD procedure, using a proof of concept of NEF called the NEF emulator. This tool, what it does is to simulate a path and gives the information, the same information that it would be offering if it was a real path. It's exactly the same, but it's emulate the path, the moving is simulated. That's the reason why it's called NEF emulator. In that sense, we can recreate a real 5G infrastructure. We can configure the path the UE will be following, in this case, the car, and we can retrieve the information of the location of the car, the GPS coordinates if required, or the SLID from the car. The other demonstration is the demo 2. It's the opposite. It's like, okay, we can retrieve information from the net in a standardized way, like it will be a full 5G, but we are going to try this in a real 5G environment. But instead of retrieving the information through the net, retrieving directly from the cell. In that sense, we retrieve the current cell ID from the 5G modem, so we know where we are and where we need to deploy the new component. The most important part of this is the functionality is really to get information from a real net when available, as we have the both options. We have it at fully compliant with a 5G scenario, so when a real net is available, we only need to change it, and it's interoperable with no needed required, no change required. So this is the new architecture, the new change with there's no SDN controller required anymore, as the controller is asking directly to the network exposure function. This is the equipment that use it in the simulated one. And this is the schema of the first demonstration. Basically, at the first stage, we have in our use case, we have a manager and aggregator which are the components in charge of managing everything, and the virtual view. In this case, it's already deployed, but it's not busy. It's available for any car. So when a car appears, it's assigned to the virtual view that was already available. So it connects, when it's connected to the network for the first time, it's automatically assigned to the virtual view. So when it's registered on the net emulator, and the OVU is binded to a previously defined path, simulating the same path that the real one is also going to do. In that sense, the car is starting to move. When it has moved enough to the point that the handover of the cell will be performed, the network application realizes through the net emulator that it has changed its position and it needs to launch a new VOU. So when that happens, a new virtual VU is requested, deployed, and therefore attached to the OVU. In that sense, it's like the old virtual VU is migrated. It's not migrated per se, but you create a new one, and migrate all the data. So it's a process absolutely transparent for the car. The car doesn't know that anything has changed. So this is the path followed in the real testbed of our campus. Basically, this you can see in red the two main points, and the path that the car is going to follow is between the two of them. This was the equipment used, the real OVU with the 5G modems. And again, here the path with the two antennas between which the cars are going to make the handover. So again, it's the same scenario as the other one. The car is the OVU connects to the network, so it's assigned a virtual OVU. The car moves. In that case, the car is actually moving. It's detected that it has moved, so a new view is deployed and assigned to this one. Here you can see in the monitoring data we gather when we execute this demo that when the OVU changed the position, the migration was triggered. And here you can see how this really happened because the CPU had the movement is instantiating the OVU. Basically, you can here and see the information. And that's all from my part. I don't know if there's any doubts, any questions, or if all the questions are at the end.
We've mainly allocated questions at the end, but if there are any questions, I think there's time for like 5 minutes of questions if people want to ask anything. If not, we can continue.
Okay. Thank you so much.
Thank you, Anna. Okay. Right, so we shall continue with Christoph's presentation from Yogoko. So Christoph is the head of innovation projects at Yogoko. He's an expert in communication systems for road and rail transport. He has 12 years of experience in industry as a systems architect and technical manager. He also was an assistant professor at IMT Atlantic for 8 years before joining Yogoko. His main areas of interest include radio communications, networking, virtualization, and cybersecurity in the context of mobility applications. And he has a lot of experience in, collaborative projects, working on collaborative projects within the European environment and France. That is. And I'll let him give any other details that he wants.
Thank you very much, Chris, for the introduction. Let me share my screen. Okay. Do we have something to annotate? Oh, okay. So yes, my name is Christophe Couturier. I'm the head of innovation at Yogoko. Yogoko is a French SME. We are supplier of connectivity solution for the ITS, Intelligent Transportation Systems. And the title of my presentation today is 5G, an enabler for CITS deployment. C in front of ITS means collaborative, so collaborative ITS. Because at Yogoko, our goal is to help CITS application developers to set up the connectivity that they need for their application. So in this presentation, we'll show how 5G and more precisely virtualization and edge computing can speed up the development of CITS application. So first, a bit of vocabulary, just to make a clear distinction between CITS and V2X. CITS, in my vision, I think it is shared, is an umbrella word gathering a large number of use cases and applications like road safety, traffic management, parking management, routing of vehicle, energy management, smart cities, and a large number of other applications. And to work, collaborative intelligent transportation system rely a lot on data exchanges, so about networking communication. And this is where the term of V2X is used. V2X is often used to identify all kinds of communication needed by CITS. But for today, and for the sake of simplicity, I will reduce a little bit the scope of what I mean by V2X to what I call direct communication. So for those of you who know that, it's what is covered by ITS G5 or C-V2X, or even by extension, if you want, by Wi-Fi, Bluetooth, etc. So all what enable direct communication without relying over an infrastructure. And by opposition, I will call in this presentation V2N, so vehicle to network, other communication solutions that rely on the infrastructure. So typically the UU link of 4G or 5G. As a disclaimer, I have to mention that this distinction depends on the audience and on the people who are speaking, because if you take the wording of, for example, 5GAA or 3GPP, V2N is included in V2X. But for today, I will make this distinction because I need that to explain you. And there is a reality behind that. It is because also we have a complete different communication scheme when we use V2X than when we use V2N. And since it is a different way of establishing communication and managing it for the developer of applications, so for our customers, it has a huge impact because these two kinds of communication don't behave the same at all. So the question we want to answer at Yogoko and today is how to deal with this heterogeneity. So the problem of heterogeneity, where does it come from? It comes from the fact that we have direct communication solution, so what I call V2X today, or also centralized communication, so typically 4G, 5G, typical communication, and also a lot of other communication like LoRa, for instance, for IoT, or smart grid protocols like 15118 and other protocols related to transportation applications. So the purpose today is not to go deep into these differences, but just to mention that even in the direct communication solution, we already have at least 3 or maybe 4 standards, because, for instance, the one which is currently widely deployed in Europe is ITS G5, and its counterpart in US is called WAVE. But so this is something that is based on the Wi-Fi 802.11. But there is a competing standard from the 3GPP that is called C-V2X, which is basically based on the LTE. And there will be, in the near future, the declination based on 5G, which will be called NR V2X. So you see that for the developer of application, he has to handle several standards, several possible ways of communicating with devices. And the point is, if you want to, one device that is equipped with ITSG5 cannot discuss directly with something in CV2X or in 4G. So we need somehow to make all these devices able to communicate between each other and with the infrastructure. So one part of the solution to this problem of heterogeneity is standardization. So this is a representation of the CITS communication stack. It is a simplified one that we use at Yogoko in commercial presentation, but just to explain how it works. At the lower layer, you have the communication technologies like 4G, 5G, so UU links, or 802.11p, which is the basic for ITSG5, CV2X from 3GPP we already mentioned, and other technologies, including typical Ethernet or IP communications. And obviously, all these technologies are implemented according to standard, but for the developer application, it's impossible to cope with all these standards into a single application. And we add, on top of this technology, the CITS communication stack add a certain level of services. And the higher you go into the stack, the higher the level of services, like in every communication stack. And the good point is, the higher you go into the stack, the lower number of standards you will find. So the easier it is to make the interconnection between the standards. So our proposal, and this is the typical proposal of networking, is to go up into the stack and to make the interoperability at higher level in the stack. And if you look how it works in the internet, it's exactly the same. You go, if you want to interoperate between an Ethernet device, a Wi-Fi device, or a Bluetooth device, or a fiber optic connected device, you will go up to the stack and the interconnectivity will be achieved at the IP level. So this is what we intend to do in order to ensure interoperability. So doing so, we will face some challenges, mostly because the way it is represented here is a simplified representation. And even if we have unified APIs in certain standards, we still have different standards at this higher level. For instance, the standards are not the same in the US or in Europe, for instance. We also have some issues regarding security, but I won't go into detail today on that. And also another issue is that these standards only deal with, for the moment, only deal with CITS under the vertical of automotive, but we don't have the same standard for instance, for smart cities. But still, the benefits of having interoperability at higher level in the stack is that first, we make an abstraction of the radio technologies. And very often it is said that the higher you go to this in the stack, the lower, the higher the delay, because you have to go deeper into the core network and you have delay related to that. But with 5G, we will see that with the MAC, with the mobile edge computing or multi-access edge computing, call it as you want. With the MAC, we can still achieve this interoperability quite low into the architecture and keep a reasonable delay. And the other benefit is that the higher you go in the stack, the more friendly to the programmer it is, and the easier it is to do the interconnection with other silos like smart city or SCADA or whatever transportation system. In addition to the standard, another part of the solution is 5G. And what are the promises of 5G? The promises some are already up to here today. Some are still promises. We are still waiting for some of them to arrive, but they are already standardized actually. So we are two families of promises, some at the radio and access level. And this is already true a reality for 5G, typical 5G over UU. We have a better throughput, we have a lower latency that enables to run automotive applications over a typical UU connection of 5G. We have also a new direct communication, so PC5 protocol for V2X, which we called NR-V2X. It is not yet available as a product, and it has the drawback that it is not directly compatible with the former C-V2X. But still, this will enable very future use case, what we call day 2 use cases that are very demanding in resources. So typical of this kind of use cases is remote driving, see-through, so transmitting videos in real time, platooning, etc. So this is for the radio and access level, so better throughput, better latency. And we have also innovation with 5G at the architecture level, which enables slicing, so which is good for QoS and resource sharing. And also mobile edge computing, which is where we as 5GAS put our network application or net apps or NApp. And the point is that since it is near to the field, near to the base station, we can achieve good latency and better and quick scaling of our applications. And last but not least, we have with 5G a tighter integration with the 5G core. As Anna said, we can interact with what we call the NEF, network exposure function, which enable us to retrieve some information from the network, like the location of the devices, like the quality of the radio link, etc., etc. So what did Yogoko implement in the scope of 5GAS? We implemented basically two networks applications that are called virtual RSU and central RSU. So these slides, you need to read it bottom up. So we'll start with the VRSU for better understanding. So VRSU is an application that is here in the far edge of the network, typically near the base station in the eNode B, GNode Bs, which provide low latency. And with the aim to do two things. First is to interconnect devices with the network, so like traffic lights or cameras or smart variable message panels, things like that. We achieve the interconnection with these devices, and also with radio, what I call radio heads, which will actually broadcast the signal, the radio signal, either in the former ITSG5 or in the C-V2X format, or in the future NR-V2X format. So basically, the promise of 5G is that GNode B will be able to send C-V2X or NR-V2X messages. This is not the case yet, but we made the demonstration in the scope of 5GAS last year that we are already able to integrate such kind of radio heads that we provided as Yogoko with the network application. So it is already feasible, even if there is no commercial products from the big industrial like Ericsson, Nokia, etc. But we are still able to provide that. And the other NetApp is what we call central ITS station. This is these two clouds here. So it is also a NetApp, so it can be deployed either in the edge or in the cloud of the network. And it is basically a gateway to other systems like road operation centers, car manufacturer clouds, fleet managers, service providers like a transportation company, things like that. And also since it has an IP connection to the internet, it can connect the mobile devices. So this is a huge advantage because any 4G or 5G enabled device, so either a smartphone or a car with 5G modem, can interconnect. You can connect to the CITS NetApp. And through the CITS, it can discuss with other V2X, standard V2X devices. So CITS bring interoperability. And obviously, since it is a NetApp, it is auto-scaling based on the load of the network and also on the location of the devices. So this is what we do, and this is how we can achieve an homogeneous access to any kind of device for application developers. And we can also implement here some specific gateways if some of the third parties don't use the CITS protocol. We can implement their protocol into the NetApp in order to include them, to give them access to the CITS world. So as a conclusion, so Yogoko's NetApps over 5G enables very easy CITS interoperability by connecting any kind of device, so vehicles through V2X or V2N, so 4G or 5G, any kind of infrastructure equipment like traffic light, camera, etc., any kind of smartphone, so typically for vulnerable road users, so pedestrians, cyclists, e-scooters, etc., through V2N, and even any other services from the internet using standard IP connection. And so this enables very easy development of the application for our customers. And since we are integrated into a diverse pipeline, it also speeds up the integration and the testing process. It enables, as any cloud application, it enables a smooth scaling and of the application that will follow the commercial ramp-up of the services. And it also enables new services, since we are not talking we are making the bridge between the CITS world, the automotive world, with any kind of other vertical like PPDR, smart city, smart home, energy management system, etc. And this is made possible thanks to five GASPs, where we have defined common deployment procedures for any kind of telco and for any kind of vertical or market vertical. And 5GASP also brings us the advantage to showcase that all that is already possible. So it is available on the market today, thanks to the 5G and the virtualization benefits. So that's my conclusion. And thank you. And I can answer to question if you want.
Right. So actually, that is perfect timing. Thank you very much, Christoph. And we actually have one question for Anna. She answered in line, but if you want to, you can develop.
Sure. The question was, what was the purpose of the virtual view and the use cases involved? Basically, the purpose is that as the physical view is located in the car, it's moving, so it can be in some moment located in a place without coverage or with low signal, etc. So basically it could be a moment when it's not available. So the idea is to deploy a cache, a digital twin located in the edge, at the edge. In that sense, when you need to access to the physical view, instead of accessing directly to it adding more latency because it's a link that it's not as much reliable as something located in the edge. You can access directly, it's available every time, etc., etc., etc. So it increases the performance and the availability of the services. So in any service or any circumstance that you need to retrieve something or connect to the physical view, for example, to retrieving the monitoring data gathered there, instead of accessing the physical one, you access the other one. I don't know if I think it's the question is solved. If not, please write any other question that you would have.
Thank you very much, Anna. We have another question actually in the meantime. And I think this is for you, Christoph. I think if you want to, you can read it out and answer it.
Okay, I think you speak about the question of Mariama. So by the way, hello Mariama, because we know each other, so it's really nice to see you. So the question is, what are the challenges, if there are, faced to connect VRSUs to field devices like traffic light controllers, and how to deal with legacy equipments? So maybe I can share my screen again. Back to my slide. So yes, I would not say that there are challenges, but maybe I can try to explain a little bit more how to interconnect, for example, a traffic light to a VRSU. First, we can explain how it is done today. Today, we attach a physical device that we call RSU to the traffic light. And we have we are working with traffic light manufacturer to implement the correct interface between the RSU and the traffic light. And with this RSU, the traffic light can broadcast its signal phase and get priority request by radio. But it is limited to the surrounding where we can broadcast the signal around the traffic light. So typically in the radius of 300 meters, something like that. With the VRSU, we implement the same interface as we already did with the RSU, but over an IP link. So here, the dashed line, we can discuss how it can happen, but basically we have two IP connected devices. So typically it will go through, actually it has to go through the internet, then come back to the VRSU, but it is clearly achievable. And this is how we manage the connection. So, and for the next part of the question, how do you deal with legacy equipments? Actually, it is, I would say, maybe simpler for legacy equipments to attach to a VRSU because you don't require any hardware equipment, only an IP connection to any kind of internet. But very often, this kind of device have at least a 4G connection or even a cable connection to a control center. So usually it is possible to connect, to get the phase of the traffic light in real time over the internet and to connect to the VRSU. So maybe it is easier to do even with a virtual RSU because at least it is cheaper for the manufacturer because you don't need to deploy additional hardware on the field of the device. I hope this answers the question, but can elaborate a little bit more if not. Okay, thank you, Mariama.
If there are any questions, please feel free to ask them. We still have 5 minutes for questions if needed, but we can also continue with the panel session. I will stay for like 1 or 2 more minutes so that we have anyone outstanding.
I think we should go back to the first question from about the FNTP and security. Maybe the slides from Christophe showing the architecture could be useful to give an answer.
Absolutely. Christophe, the floor is yours.
Yes, actually, I'm not sure to understand the question. You mean this slide, I guess? So to be clear, this slide is it's not meant to be a technically accurate. It's just to explain with big blocks how it works, and it's not the purpose of going into the detail. Actually, otherwise we have more detailed slides. So I don't know exactly what to answer to that. Maybe Thierry, if you want to add something.
Can you hear me?
Yeah. Oh, yes. Please
Okay,
speak up. Yes.
I wasn't sure how this was going to work, but now it works. Yeah, that was only a recommendation that you use FNTP, since WSMP is a subset of FNTP, and FNTP was developed by ISO, and it's a much better protocol. That was the only suggestion. The second observation is that security that we've deployed in the system is end-to-end. We don't use network security. Not that you can't use IPsec if you want, you can, but we don't depend on it. Who's we? Everybody developing ITS services on planet Earth. So the SCMS you have deployed in Europe issues certificates to applications, not network protocols. And applications use them. So there's end-to-end security. That was my only point. It's important to understand.
So
One
can you
final
just
thing.
introduce yourself?
Oh,
Sorry, can
my
you
name
just
is Dick.
introduce yourself? Yeah, thank you.
Sure. My name is Dick Roy, and if you want to know everything about me, just ask Thierry. The other final thing is virtual RSUs have been attempted. We have tried them here in Northern California, over in the East Bay, and with a company called Verizon. You may be familiar with that, one of the largest cellular providers on planet Earth. And they generally fail. Why do they fail? They don't scale, and no one wants to get signal phase and timing through a subscription service. No pay for play here. Spats and maps have to come free. And you need to figure that out. That's why the SPAT map application has requirements set to station management, which state it needs to be a free path. Whatever you choose, don't charge me. And then you'll set up a path that doesn't involve a UU interface for which T-Mobile's going to get paid. That ain't happening.
I fully agree with you, and this is why for the last 8 years, or at least for the beginning at Yogoko, we were really pushing direct communications. But the point is, we are more and more asked by the customers to get V2N connection. And the main reason is that for the moment, how can you connect a pedestrian to or a bike to a traffic light, and you can't do that because we don't have cheap V2X connectivity, and this is not the case with V2N, and people already have.
We do have cheap V2X and V2N communications. It's called G5. G5 is Wi-Fi. You know how cheap that is? 50 cents a module. It's the cheapest thing on planet Earth, which is why it's in over 10 billion devices. And it's usable. You can also use Wi-Fi. Can you use cellular? Yes. Every OBU on planet Earth today that's out there, including the 2 million in Europe, VWs, have LTE connections. They are considered, that radio interface is a UE to a network, an eNode B. And is it useful? Yes. Do we distribute certificates over it? Yes, sometimes. Are we going to use it to send CAMs and SPATs and maps? Not on your life. Not happening. Because nobody wants to pay for it. That's the whole point. And yes, there is cheap access to the network from every OBU today.
Honestly, I don't agree, because we have experimentation here in Europe about GLOSA, for example. So green light speed advisory that works only on V2N. And the reason is, since people already have a smartphone, or in the car there are already 4G modems, you don't have to pay an extra. You already have the connection. You already have to pay it for that. So this is a way to access a service that is either not available because you don't have a V2X modem for now in the smartphone, or because just you are not in the range of the RSU. Because if you are 500 meters away from the traffic light, there is hardly chance that you can receive the signal.
Johannes had something
we've
to
demonstrated kilometers, but you know, that's
Yes, but
that's an RF issue.
we also did that in kilometers,
Right.
but not in cities.
Yeah. Everybody's done it, so it's no big deal.
So we have some input from Johannes now. We will continue like the conversation afterwards as well, and let's stop the discussion there to start with. Have some input from Johannes, who is one of our panel speakers, and we can continue the discussion after within the panel discussion as well, if you want it as well, especially since you, Thierry, are part of the panel as well. Thank you. Johannes, you have the floor.
Okay, shall we start with the panel? Okay, and also maybe I can use, because I raised my hand.
Actually, it would be better. Yeah, so like let's just start with introductions. So you can start, Johannes, and then we can continue our discussion. Actually, that is a good handoff. Yeah,
exactly. It would be really a good handoff from the previous section. So thanks, first of all, for the invitation here for this panel discussion. I'm Johannes Springer. I'm responsible for 5G automotive topics at Deutsche Telekom, and also representing Deutsche Telekom in various fora, including 5G Automotive Association, where I'm also working as a 5G AA Director General, together with my colleagues in the Executive Committee. So, you know, my major topic at Deutsche Telekom is mainly to make sure that we are providing the right network capabilities for automotive use cases. And many of the capabilities are already mentioned in the previous presentations, like edge computing, quality of service topics, network slicing, quality on demand, how to make use of out of these nice network exposure functions as defined by 3GPP. Most of you should be aware about the Camara initiative we have launched with various mobile network operators around the globe to provide network as a service interfaces to the various application developers. So I wanted to make a comment with respect to the previous discussion, because, you know, SPAT map, for instance, take this virtual RSU topic, and SPAT map information is already available in many services around the globe within commercial services. Is somebody paying specifically for SPAT map delivery? Definitely not. You are completely right. But if you are paying for an overall service where the SPAT map is integrated as part of a V2N part, the delivery part via the UI interface, that's already a reality. It's a reality. Nobody should say it's stupid, it's not worth. No, it's there. It's a reality. You can buy it in an Audi. It works in 20 cities in the US. It works here in several cities, also in Europe. If you go to the Netherlands, you get SPAT map information, a closer time to green information via your Flitsmeister app. Do you pay specifically in addition to to a closer time to green service? No, but it's part of your Flitsmeister service. You are already paying maybe an additional fee or something like that. That's part of the commercial relationships of Flitsmeister to their customers, but it's a reality. It's there, it works, and it works perfectly with thousands of smart traffic lights intersections in the Netherlands. So, this is not something which is a dream or which is something wishful thinking or something like that. No, it's a reality. And it's continuously growing, this kind of ecosystem, with respect to various use cases, which are creating more and more demand, of course, on latency, on availability of the networks, and so on. And the mobile network operators around the globe, including Deutsche Telekom or also our competitors like Verizon, are doing a lot of things to make sure that these use cases are, let's say, near 100% available around the globe. That's something I wanted to make very sure, very crystal clear here in the group. So the two presentations of Anna and from Yogoko, they were great. Let's say provided great foundations for these kind of business models and infrastructures, which will come and which are already there in one or the other market. So with that, I want to leave it, and of course happy to discuss further in the panel discussion. Also, of course, also with other colleagues here in the audience.
Okay, that's fine. Thank you very much, Johannes. That is very nice. So we can continue with the introductions of the panelists. Since Thierry, you started the conversation, you can introduce yourself, and then we can let Andre introduce himself as well. And we can start the discussion, as I know that all of you really want to get in on it. Thank you.
Yeah, sure. Okay, so thank you for the introduction. So yes, I'm Thierry Hart. I'm the co-founder of Yogoko, and so we created the company 9 years ago, and on the foundation of providing extended connectivity using multiple communication channels, including, of course, cellular and ITSG5. And I'm also very much involved in standardization activities related to cooperative ITS and other type of ITS services. So let's go to the introduction of the other panelists.
Andre, you have the floor.
Yeah, hello. My name is Andrei Radulescu. I'm the co-founder and the CTO of Neobility. Neobility is a startup. It was founded in late 2019 with the vision to accelerate urban mobility by improving the capacity and speed of movement for city residents. How are we trying to do that is by creating a multimodal platform for cities to adopt in order to optimize public transport. And we have two products. One is called Urban Air. Urban Air is an aggregator like that you can use right now. It's an app that you can take from the App Store or a Play Store, and you can use it to use any mobility alternatives, let's say, compared to public transit, for example, car sharing, e-scooters, and every service like this. And besides this, we have a second product that is called NeoBus, which is a demand responsive transportation service that we are building alongside the 5GAS consortium, which we are a part of. As for NeoBus, I can also tell you that we are reaching 5G. Initially, we had no experience with 5G, but during the 5GAS project, we started making this app a 5G cloud native application that is using 5G infrastructure. And this way, we are delivering better services to our customer and building a real-time distributed vehicle routing problem optimizer engine that runs on Mac and multiple servers closer to the user. And besides this, we are trying to use the 5G net right now with an emulator inside the 5GAS platform for getting the UE location and tracking the UE devices between cells, and in order to optimize and adapt the actual algorithm to stay efficient. This is my introduction.
Thank you very